Welcome to the Simulating Motion and Control tutorial here at SciPy. My name is Jason Moore. I'm a professor at UC Davis in the Mechanical and Aerospace Engineering Department. And we are going to talk about how to simulate rigid body dynamic systems like robots, people, etc., and how to do a little control work all in the realm of Python. I have two co-instructors here, and I'll let them introduce themselves.
Hello, I'm Robbie McMurray. I also work at UC Davis as a research engineer. Most of my research is in heating and cooling for Western Cooling Efficiency Center at UC Davis. I have a little bit of background in wind turbines and vehicle dynamics, and that's sort of why I'm here.
And I'm Brandon Milam. I'm a graduate student at the University of Florida in mechanical engineering. And I'm working on PyDy with Google Summer of Code this summer.
Okay, so they'll be here to help you out, and we're going to switch up teaching to you so you don't have to listen to the same person each time. Just a few things on the background. We have a project called PyDy, and PyDy stands for Python Dynamics. And it is a sort of overarching tool that brings all these things together to allow you to do various analyses. And we're going to get to use that today. It's about, I don't know, 6 years or so, 6 or 7 years old at this point. We've been helped out by Google Summer of Code many years, and Brandon is one of our newest students. We also use this material when I teach dynamics in my undergraduate and grad courses, and we have students that work with it and grow. It is backed up by one of the main packages in the SciPy stack, which is SymPy. The tutorial this morning, did anybody take the SymPy tutorial this morning? Okay, great. So you're going to have a good intro for some of the things that we're going to do. SymPy is a computer-aided algebra system written in Python, and it will solve symbolic algebra, symbolic calculus, linear algebra, et cetera, and we use this tool to do the work that we do in dynamics, and you'll get to learn how that is. So this is sort of an advanced tutorial that uses a lot of the scientific Python stack tools, from NumPy to SciPy to IPython, and primarily SymPy, and we'll see how that symbolic tool set is used mainly. Okay, so why don't we take right now, let's take a few minutes, introduce yourself to your adjacent neighbors, tell them why you like Python and why you like simulating motion control of various objects in life. Okay, so take a few minutes, introduce each other. Okay, well, thank you all for being here again. And you're going to get to work with your neighbors too as we move through the tutorial, so that intro hopefully will set that up. I want to point out, so we have an Etherpad going here. You may have used these in software carpentry workshops or other workshops around SciPy. This is a collaborative note-taking space that you all can take notes in. At the end, you have a nice document with information about the tutorial. I've started it with a few links here. You can change the color of your name over there on the right once you go to the link at the top. And there's a chat room that Robbie and Brandon will be monitoring. So if you have a question while one of us is speaking, you can chat it in there, and we'll do our best to respond. Okay? So we'll use that Etherpad, and we'll paste things in there too if we need to share links with you and stuff, so you don't have to. So you can just copy and paste them yourself. So we use that as a tool. Let me get a few questions too. How many people have had high school physics? Everybody, pretty much. College physics? All good. What about grad level physics? Okay, good amount. What about in mechanical engineering, like dynamics, undergraduate dynamics classes? A few, okay. And then graduate level dynamics classes? Okay, a handful. Good. Okay, so that's good. That's about standard for the conference here, and we will try to reintroduce many of the concepts to you, so you'll be refamiliarized with that. How many people have worked in Python? And then with the SciPy stack, like NumPy, SciPy, IPython. How many people are familiar with IPython notebooks or Jupyter notebooks? Everybody good? Okay, so we'll be in pretty good shape on that. And then how about SymPy? Have we have any SymPy users? Just a few? Okay, good to know. About standard 2. Okay, so after the Etherpad here, let's sort of get into things. The first thing we want to do, if you had this zip file and you extracted it, I have mine in a directory here called PyDay tutorial human standing. And if I go into that directory, I'll find three files. Check environment py, a notebooks directory, and a readme. Yeah, it's going to be hard to do this. If you want to run the check environment, so if you do python check environment.py, first, if you run that and you get no errors, then you're good to go. So go ahead and do that. If you get an error, raise your hand and Robbie and Brandon can come by. So after you check your environment, if you change directory into the notebooks directory, this is where all the content is. We're going to walk through several Jupyter notebooks that you can execute and play around in. We're going to skip the 0th one. You can start the Jupyter Notebooks server by typing Jupyter Notebook inside that directory. And it should fire up your web browser with a Jupyter Notebook instance, and we'll be ready to go. Okay, so in the process here, we're going to also use another little mechanism. We've got these sticky notes that Robbie and Brandon are going to pass out. And how we're going to use those, you're going to get a red one and a blue one. And when you're doing exercises, you put the blue one on the front of your notebook or your laptop if you've completed the exercise, right? And that'll give us a signal to know when you're done. If you need help, you put the red one up. And then the help, whoever's not teaching, will come around and help you with that particular assignment. Okay? So they'll pass those out, and we'll make sure we use those during the exercises. And finally, we'll collect feedback from those go ahead. We'll collect feedback from those at the breaks. How many breaks would people like? Is 1 in the 4 hours enough? Raise your hand if that's enough. Raise your hand if you'd like 2. 2 breaks. A few people. We can do 2 breaks then. We'll try to break around after an hour and a half or so, and then a little later. Okay, so we'll do 2 shorter breaks in this point. What's next? I think those are all the main intro things. Do I have any questions at this point about the introduction? So I want to show one thing. If you go to New Notebook and open up a notebook, we have exercises, and they'll be signaled by they'll look something like this in the notebooks. You'll see a title, some text. Below it, you'll have an empty cell where you get to try to do that exercise. And then below that cell, there's going to be a command that looks something like this. Right? And this, if you're having trouble with the exercise and want to see our solution, you can execute that cell by pressing Shift-Enter, and it will load in a solution that we made for that exercise. And then if you select that cell again and press Shift-Enter, it'll execute that, okay? So if you ever get behind in the things, the solutions are always there, and you can execute that solution and keep up with things. I recommend, though, give it a good shot before you just look at our solutions. But they are there to help you catch up and see what you're missing, okay? But we'll give you ample time to go through those. So that's. I'm going to be using the board in a minute, and after we do that, we'll lower it back down. Okay? Thanks. Any other questions? All right. So let's go ahead. We're going to skip notebook 0, as I said. It sounds like everybody has good familiarity with Python. And we're going to start with this dynamics overview notebook. So if you open that up, I don't know how the font size is. I don't know if I'm actually increasing it. I'm going to take away some of these toolbars so we get more space. Okay, so what we're going to work on today is primarily rigid body dynamics and how to simulate motions in the macro world. These systems, like a vehicle from a human body to a quadcopter, are all governed by Newton's laws of motion. And so we're gonna do an example system today to see how you would set up a problem like that, simulate it, and then try to control it. So if you remember Newton's law, second law of motion is approximately force is equal to the mass times the acceleration of the system. And this law governs everything in our sort of macro world, from how we move, to how we throw a baseball, to these vehicles, to even the planetary motion, et cetera, et cetera. So it's a big deal, and we can use that to predict all kinds of things about motion. And once we can predict the motion, we can also try to control it. Okay? So key things here, these are all vectors, right? So if you see these cap letters with the arrow on top, we're going to be working in vectors. Everything in the three-dimensional world is going to be described by vectors, from the forces that apply to the system to the positions, velocities, and accelerations that we're going to see of that system. It's important to note, too, that this is fundamentally a relationship that is a differential equation. We have a second-order ordinary differential equation where we try to find out what the position of some object is over time, given the relationship that the force is proportional to the acceleration, right? So we start with that, integrate twice, and then we can find out about how that object moves in space. So that's what we're going to do today. We're going to start with a description at the force and acceleration level, integrate that equation and twice so that we can see what exactly the position of this system is through time. And to do that, we need to remind ourselves about vectors. Okay, so these the key parts to creating and building these models are being very precise and careful about how you use vectors in describing the position and locations and accelerations of primarily the mass centers of the different bodies that are involved. Okay, so some of the things, right? We have direction. All vectors have direction and magnitude, and they're usually drawn as an arrow. If we have since we're working in 3D and we got a 2D screen, vectors out of the page will be a circle, vectors into the page an X. There's a few other details. We use the hat symbol as a unit vector. So if I have a vector V here divided by its magnitude, I will get a vector of unit length. You'll see that symbol a lot. The two bars represent the magnitude of a vector. So we're going to use these vectors for all these kinds of descriptions of these things. So let's go ahead and start. The first thing is, once you have vectors, you can do lots of operations with them. So we're going to go through some of the basic vector operations that you may remember from vector calculus to get a little intro before we actually jump into the real problem that we're going to work on. So given a couple of vectors, you can add them together. One way to visualize that is putting them end to end and seeing what the resultant vector would be from the tip of the first one to the tip of the second one. So here we have some notebook cells now that are going to start to import some of this software we need. The primary package that we're going to be using to do sort of symbolic vector manipulations is SymPy, and we have a package in there called mechanics that's going to provide all of this, all these vector tools. There's a few other things here too to give us nice, pretty printing. SymPy has a rich printing interface, so when you print in something like the IPython notebook, you're going to see nice, rich mathematics and be able to read those just as easy as you did in a textbook. Okay? So a go ahead, you can follow along with me, execute these cells. Feel free to play with things. If you remember, you can insert cells below, right? If I wanted to explore that object, here I created something called a reference frame. I can use the question mark to try to explore what that thing is. It'll open up a help file. So feel free to, go around and edit things while I go. Okay? Not good sound? I'll do my best. You guys should get one of those little mics that stick to people. Thanks. So the next line here, we're going to bring in some symbolic variables from SymPy. I'm not going to be able to do that. We're going to bring some symbolic variables from SymPy into the space. So there's a nice convenience import here from sympy.abc. You can bring in all kinds of Greek letters, all kinds of standard alphabet letters, etc. And the key thing here is that we're going to construct vectors using unit vectors, right? So I created a reference frame in that line 2, and that reference frame has a unit vector, 3 orthogonal unit vectors associated with it, right? Each one of these unit vectors are perpendicular to each other and of length 1. And I can access them by doing in.x, in.y, and in.z. So these are the constitutive building blocks of creating complex vectors. So those are unit vector objects, and then these C, D, E, F, G, H, they are scalars, right? So if I multiply a scalar times a unit vector, I will get a vector in that direction of the unit vector of that length. And if you see here, I've created a vector called A, where I multiply a scalar C times the unit vector in X times the unit, and D times the unit vector in Y, plus E times the unit vector in Z. So this is a vector in 3D space with the coordinates, X, Y, Z coordinates, C, D, and E. And you can see that those vectors print nice and pretty. You can also, there's a method on a vector called toMatrix, and it will put it in a linear algebra form. So maybe you need to work in those vectors in linear algebra. Notice that I had to tell it the reference frame in. So I said, please tell me the coordinates of this vector in that particular reference frame. It's important to note that we store vectors, as I have in line 8, because, and we attach reference frame information. I'm going to go into details about what a reference frame is and why we need to be careful about knowing what reference frame we've defined our vector in. If you notice in line 9, this thing is not aware of what reference frame it's associated with. It's really just a column matrix of 3 scalar values. And it's very important that we know which reference frames that we define these vectors in. And we'll see that a little bit later on. But this gives you 2 representations of a vector, one in matrix form and one in this sort of rich form with the unit vectors of that reference frame. Okay? So I can create multiple vectors in space. I got A and B available. The vectors have a lot of methods associated with them. For example, I can easily calculate the magnitude of that vector. Right? So the square root of the squares of all the measure numbers of that vector equal its magnitude. And then finally, you can add vectors, right? So I can see if I have 2 vectors that are in this in reference frame, it'll simply add the scalar values that prepend the vectors there, okay? So that's addition and getting a magnitude, how to create a vector. And then finally we have scaling. So you can multiply vectors by any kind of number or any scalar value, whether it's an integer, a float, or other SymPy variable. So I can do 2 times a vector to increase its length 2 times. I can negate a vector to make it go in the opposite direction. Okay? So these are the basic how to create vectors and how to do some basic manipulation. So now take a few minutes, and you can work with partners while you do this. I encourage that. We've got an exercise here that asks you to create some vectors and do a manipulation with them, okay? And if you remember, so you can do your work in this cell here, and if you get stuck and want to see a solution, you can execute that second cell. But go ahead and give it a try. Remember to use these sticky notes, right? Once you're done with this exercise, put up blue sticky note. If you need help, put up a red. And is that red sticky back here? You need help, maybe? No? Okay, good. Okay, so give that one a shot. See if you can create some vectors with SymPy and do a little manipulation with them. And we'll give you a few minutes on that. Okay, I think I've got a pretty strong majority of blues now. So if we take a look at, I'm going to load that solution and execute it. It's able to, so what I do is I created a reference frame to start with, right? That's the first step in creating a vector. And then I created the 3 vectors trying to follow the explanation in the bullet points 1, 2, and 3. I first used, we have a vector that's at 45 degrees from the x-axis. So I use cosine and sine to give those 2 correct scalar values for the x and the y unit vectors. The second vector is in the negative y direction, and it's of length 10. The third vector is slightly incorrect. Can somebody tell me where I goofed up there? Yeah, so I did the rotation from the x-axis. So this was how the first one, this is how the second one was incorrectly defined. It's supposed to be from the y-axis, so something more like that. And then you would change that solution slightly, just to give it a, we've got a negative sine of theta and a positive cosine of theta. Okay? So if I execute that again, that's the correct solution. So that's what you should have gotten there. So you can see that it gives a full symbolic form of the situation, and it also automatically, cosine of pi of 4, it throws that in there, the square root of 2 over 2 for you. So this manages all of our vector algebra, okay, that we do. Any questions there on basic vector introduction? Yes?
Quick question. When you calculate the magnitude of the 3 vectors, why doesn't it reduce it to as much as it can be reduced? For example, I write magnitude of the first vector is square root of x squared.
Yep, so very good question. So can somebody from the SymPy tutorial tell me why that is? What's your name? Okay, she asked, why does the vector, if I ask for the magnitude of the vector, why is it that it doesn't give me in the simplest form possible? And can you answer that for us?
I think you have to say simplify it, but then they'll have to know that the number is real.
Yeah. So there's some details there, yeah. SymPy in the background is not going to put things in the simplest form because it's not actually the most computationally efficient form. And the act of simplifying in a general mathematical expression is a very hard computational problem, right? So you don't want to waste computing energy if you don't have to trying to put it in the simplest form. For simple expressions, this works. So if I do something like, if I had V1, that magnitude, so in this case, it won't simplify 2 because of the second thing you said. It doesn't know that L is a real number. By default in SymPy, everything is a complex number. Okay, so that's the other detail. So sometimes you'll see things that won't simplify automatically. If I come up here, for example, and I do L equal from SymPy import symbols, and I do L equals symbols L, and then I say it's real. You can set these kind of assumptions, then it automatically simplifies, right, to the absolute value of L. Okay, so those are some details. We're working with a symbolic engine, and it has various limitations and different quirks. Okay, you can find out more details about that in the SymPy tutorial that's online, and you can find videos too. So you could go back and do that at a later date. Okay, so our vectors have all kinds of fun properties, right? We can do things like dot products, scalar products, inner products, outer products, et cetera, et cetera. In this case, if you remember, there's a lot of fun things that you can do when you can calculate the dot product of two vectors. You can project vectors. You can compute an angle between vectors, find its magnitude, compute its power. If you know force, that's et cetera. Find out if a vector is perpendicular or not. So here, if I create a couple of vectors, as usual, I can calculate a dot product. And notice that it returns a scalar quantity, right? There's no bold-faced letters there. So I can dot vector A with B, and the Euclidean inner product here is defined for these three-dimensional vectors, and I get a scalar value that represents that mathematical operation. Okay? So vectors have dot products. You can also access, we have sort of functional versions and method versions of everything. So I can also do A, since A is a vector, dot B. And that'll give me the same thing as the functional version that's available. Notice that I imported dot from SymPy physics.vector in this case. Right? It operates specifically on these vector quantities we're working in. Right? We have another dot product for matrices in the matrix module. So you have to be careful that you're using the correct one. So here's another exercise. See if you can find the angle between those two vectors that I list right there. And we'll give you a few minutes. Put your blue sticky note up, which you've got it, and red if you need help.
Yeah, right above the previous example, they're assigned to.
Yeah, so on the solution, you'll also get an error on this. You can tell which ones we all created this morning. The be sure to redefine what all the scalar variables are, because we defined A and B as a vector up here. And you're going to need to be careful about defining what A, B, and A are, right? And don't forget your blue sticky notes if you've got the solution. Okay, I'm seeing a majority there. If you check out the solution for finding the angle, you can implement that angle rule, and the error that I forgot here is from sympy.abc, import A and B to make sure they're properly defined as symbols. And we can see that we can get a symbolic result for what that angle would be using the acos function out of SymPy. Okay? Any questions on dot product? You can also do cross products, which are useful to know whether things are perpendicular, determine if two vectors are, parallel. We use them to compute moments, which we could see force times the distance. And to do dot products, it's very similar. If I have two vectors, I can use the cross function, cross A times B. Notice that you get a vector out of the cross product. You can also do A dot cross B in the method form. I didn't quite type that a little goofy. And then you get a vector which is going to always be perpendicular to the two vectors that you pass it. And then the magnitude of that vector is such. And this properly implements the cross product rule to take a three-dimensional cross product of two vectors. Okay? And keep in mind we always follow the right-hand rule. We'll see that a little more as we move forward, that you have to be careful about that. For the exercise here, it turns out that you can calculate the area of a triangle with the cross product. So I've given you 3 points that are located in space by those vectors, and see if you can find the area of that triangle bounded by those 3 points using the cross product function. You might need to look up, visit online to see if you can find that relationship too. Okay, so blue sticky notes if you got that one. Give that a shot. Remember your blue sticky note when you're done, and feel free to chat with your neighbor too to get some hints. That's about all I can fit. Okay, I think most folks have got it now. It turns out that you can find the area of a triangle by creating two vectors from a single point. So if I picked point 1 as my base point and then found the vector from point 1 to point 2 and point 1 to point 3, and I cross them, take its magnitude and divide it by 2, that is the area of the triangle bounded by those points. And I noticed that I found the vectors that I needed by subtracting those vectors to find. These are all defined with respect to an arbitrary origin, but we needed to get the relative definition of those vectors. Okay, so that's a cross product. So our vectors have any questions there? Cross product. So we've done a lot of the operations. The vectors here all obey all the laws that the mathematical rules about vectors, from distribution to doing inner products and outer products, not allowing association, et cetera, et cetera. So we have a powerful tool now here to do vector algebra. And that's going to be key for us to properly model objects in 3D space. I'll show one thing here too. So if I have a given vector, I think A was one of my vectors. If I do A dot tab in the IPython notebook, you can see that there's a number of methods associated with that vector that are useful. So you can browse through those, check them out. If you use the question mark, you can see their help file. For example, if I want a unit vector, I can do normalize to get a vector that's length 1 in the same direction of the given vector. So there's a lot of fun properties there, and you can do everything that you would expect to do with vectors. Okay?
Isn't the first point x cross x, and the cross product, the first point?
Crossing a vector with itself?
Isn't x cross x at the end?
X cross? I don't see an X.
You had it vector x cross b.
Which line?
In the middle of the screen, the crossing of vector with itself cancels it.
This?
Yeah, isn't that x cross b? X cross a cross a? Is that what you want to say?
A crossed A would probably be a, yeah, they're correct. Thank you. That? Okay, thanks for that. Yeah, that's proper. Okay, so we briefly mentioned the reference frame, right? We had to create a reference frame that provided us with these orthogonal unit vectors. And what's nice is that well, what's not nice, but what's more complicated is that we need to use multiple reference frames to help define where bodies are located, how they're oriented with respect to each other in space. So typically, you'll have a reference frame, often a base one, a Newtonian reference frame that is inertial, and everything inside that reference frame follows Newton's laws. Sometimes we use the Earth as the inertial reference frame, or an object like if a train is moving at a constant velocity, you could attach an inertial frame to that and then do dynamics relative to that. We also typically attach a reference frame to every rigid body involved, right? So if I have a car, I might attach a reference frame to that car, and then it's going to rotate and move relative to the ground, which would have another reference frame attached to it. So our vectors are pretty smart. They are aware of many reference frames that you may want to define for your problem. And I'll go over on the board here a couple of little details. You can read that section there too, but it's important to note here that any given vector can be expressed in an infinite number of reference frames. So if I see here that I can express the vector r in the A frame with the scalars d, x, and dy, but if I have another frame, B, which is arbitrarily rotated, I can also express that with fx and fy as the scalars, okay? So we can use that to our advantage to let us sort of build more complex systems and rotate reference frames relative to each other according to various joints that we might want to implement in that rigid body system, okay? So I'm going to go over a quick little example I do for my students. I like to think about a reference frame. If I have a box, simple box, and it has a reference frame attached to it, and we'll call that, I'll just call that the A frame. If I have AX, AY, and AZ, this box, I can describe all these points on that box in that reference frame. But if I have a hinge on the box, and then I have a lid that opens through an angle theta, use some different colors here, dead marker. Right, this lid can move back and forth, but maybe I'm interested in point P relative to point O, and I want to create a vector that describes where the location is of P is relative to O. Okay? So that vector, right, goes from here to here. I'll label it R from P with respect to O, like so. And when we have a joint, it becomes very useful to introduce new reference frames to try to more easily describe the location, this vector. So to do that, I could attach a reference frame here and call it by, bz, and bx, right? So if I attach that reference frame, as that lid opens and closes it, this reference frame will be attached to the lid, and this one stays attached to the box. Okay? So to find this vector, if I said that each of these sides are of length, we'll call it d, then I can walk myself through this vector. I can just do something like d times ay. That would take me to this point, and then I could go d times az. Add that. That's going to get me to here. And now I want to jump up onto the part that's attached to the B reference frame. So I can go from here to here, which is going to be in the negative by. So negative d by. And that gets me to here. And then finally, I can go in the bx direction to get to P. So I'll do P, d bx. Okay? So notice that I've created this vector now with a combination. It's a composite of different unit vectors that I use as a basis to build that. Okay? So, but there's a relationship between A and B. Does anybody know what defines that relationship typically? A transformation matrix, or a rotation matrix, or a direction cosine matrix, all same names. So in this case, it's a very simple rotation. It's a rotation in theta about negative ax. All right, so if I rotate, or bx and ax are both in the same direction. And if I use the right-hand rule, put my thumb along the negative bx direction, theta is opening that in that direction. So there is a rotation matrix that will relate vectors described in this reference frame to vectors described in that reference frame. And they typically, for a 2D rotation like we have here, the rotation matrix is always a 3x3 tensor. It's symmetric. And for a rotation like this, it's about the x. We would see, and it's about the negative direction. We're going to see a 1 in the x because there's no change in the x. We'll see zeros. If this column is x, y, and z, then we're going to see zeros here and here. And then these are going to contain something. What are they going to contain, those 4 elements in this case? Sines and cosines, right? So these is going to fill up with sines and cosines. In our case, if we look at that rotation, and we have, let me draw it this way. If I have by and bz, right? If I put my eye right here at the corner and sort of look in, I'm going to see just a 2D version of that. And those were rotated away from the AY and the AZ. So we're going to have a rotation through theta to relate those two. So can somebody tell me what the cosines and sines should be in that rotation matrix? With that relationship here? I guess. The Yeah, which reference? I'm rotating, what is the rotation matrix with B with respect to A? So in this case, this is going to be, I think B dot A, BX, B Y dot BZ. That's how you could get that. Sorry, A. One way to do it is project A into here, and I can see that AZ is made up of two components of B. It has a component that's, the length of A is 1, right? We have unit vectors. And then I have a cosine projection right there, cosine of theta BZ. And then that's positive. And then we have a negative sine of theta BY. So if I can then populate, if I have a vector, I want this to take a vector in the A frame and equal a vector in the B frame, then we can see that, I think maybe I want to write it the other way to be easier. Let's just do this version. A, B. So I'd have an AZ here, and it has no component in the X direction, a sine, negative sine theta in the Y direction, and a cos theta in the Z direction. So I would put those in there and populate this. So sort of the point of this is that this is a nasty mess, and the software here is going to be able to help you deal with that more easily without having to necessarily think about all these rotation matrices in detail. Any questions right there on what I'm describing? Okay, let's take a look at it in the code. I think it'll help. And we've got one last assignment before we'll break. If you scroll down, notice that I'm going to create two reference frames. And that second reference frame, B, I created it by orienting a new reference frame with respect to A. So I say I have a reference frame A. Let's orient a new reference frame called B through about an axis rotation. So here we would have a single axis about the BX through some angle, in this case theta, about some axis. So this method defines a simple rotation about a single axis. So it's of angle theta about the AZ axis, orient the new B axis, the new B reference frame. And then you get a second reference frame. And once I have that reference frame, I can create vectors defined in both of those reference frames. I can add them. I can do all the operations that we've done before, but notice that it keeps track of the components in each of the reference frames. I could do the dot product. Notice that we start to see cosines and sines pop in here, but I didn't have to think about that explicitly, right? This rotation matrix is actually built in once I specify the orientation of one reference frame to another. You can do cross product. You can also, if you have that vector A plus B, that's a combination, I can express that vector in a particular reference frame. And notice that the cosines and sines start to pop up at that point, right? And then the last bit here, you can read a bit about the rotation matrices. We have a method called DCM that will automatically output that rotation matrix that we just manually formed, okay? So the key part here is that we can create reference frames. We can orient them with respect to each other. And here we've just done a simple rotation about a single axis. And then you can build vectors using multiple reference frames. And it will properly track how that vector, what that vector is defined in with respect to all these rotations. You can express them in whatever frame you want once you have that relationship, and you can access that direction cosine matrix, but it'll seamlessly handle all the vectors as you go along without you having to worry about those details, as long as you set up your orientations. Question?
So when we calculated dot cross, did it use the B reference frame because that was the most recent one we defined?
So the dot, it's like when it calls dot, it says, hey, we've got these two vectors that they're defined in two reference frames. Is there a relationship between those two frames? And it says, oh yes, it is. I see where that's defined. And it uses that information to properly compute the dot product.
But the assumption is that it's expressed in B because down at the bottom you express it in A. Why did it choose to express it in B? Is that because
So the
most recent one?
The dot product operation is invariant with respect to how you express the vector, right? So if the cross product? Oh, why does it choose B? Yeah, that's a good question. So I think it just chooses the second one probably. And yeah, so you know, if we did A, comma B, B, comma A, now it's in the A frame. So I think it just chooses one of the frames by default to re-express, do the cross product, and then give you the right answer. And you can always call express in B in this case to switch it, right? It might get a little nastier. So it'll handle all these rotations and these vectors defined in multiple frames. You can express them in different ones, and it handles the DCM. So let's do this one. We've got an exercise here to take this information. You probably need to read a little. They were in those previous slides, but it's you're gonna try to set up a rotation matrix and do a vector similar to what I described on the board, and have a look at that. And after that, we'll take a break, and then we'll move into applying these to the problem that we're gonna do today. Okay? So give that exercise a shot. I would highly encourage you to go ahead and start chit-chatting with your neighbors. So pair up. Yeah, pair up. You may want to make out a little sketch like I did on the board to think about this rotation and how the reference frames are defined. So pair up, chat with your neighbor, and see if you all can determine how to create the vector that this exercise asks. Okay? So let's take about 15 minutes or so on that, and then we'll take a break. So put your red sticky notes up if you have a question, and blue if you've got the problem figured out. Okay? Okay, you should be thinking about this situation, right? We've got a laptop, I've got a keyboard with the z-axis this direction, the y-axis that direction, along in the plane of the keyboard. And on the screen, I've got a reference frame attached to the screen such that the z-axis is in this opposite direction and the y sort of down. Okay? And we're looking for the green vector here from this corner to that corner. Given that the laptop hinge opening is described by the angle theta. So that's the state you should be in. I only see a few people that have gotten it. In the interest of time, we'll solve this right now. So there's an infinite number of solutions to get the answer. The one that I proposed in the exercise solution is to create an intermediate reference frame called I. And in my case, I rotated the intermediate axis frame about the, remember here, the negative Z keyboard. So I rotated about this axis to create a new reference frame I, which I'll draw in. It'll have the same, this will be I I'm sorry. This will be also IZ. And I rotated this direction such that IY points down. Did I do 90 or pi? Oh, so I did mine opposite. I did theta first. Sorry, I rotated it such that I had IY here, IZ here. I rotated through theta to attach KY, IY here. I'm sorry, I'm butchering the description of this. IY, IZ. And then that would put Y into X. It's pointing down, so that would be like this. IX. Okay, so I first created this intermediate frame that was a simple rotation through theta from this frame to this frame. That gave me IY along this direction and IZ along that direction. And then I took that reference frame and I rotated it about Y pi degrees, 180 degrees, pi radians, 180 degrees, so that Y matches up with IY matches up with SY, and this new direction would be in line with SZ. Okay, so I created an intermediate reference frame here, rotated through theta about the negative Z direction, and then I created the last frame, the screen frame, and oriented it relative to the intermediate frame by 180 degrees. And then finally, I create this vector, and I just walked this distance to here, that distance to there, and that distance to there, where I expressed the first bit in the K frame and the last bit in the S frame. So that's the solution that you see. And you could have got there many, many ways. Okay? So I'm gonna say a few more things and we'll take a break and come back and get to the problem. So at this point, you all are in pretty good shape. We've learned how to work with vectors. And if you can properly describe the locations of points and the orientations of frames with vectors, that's the main thing that you gotta have under your belt to model these systems. The software that we have developed sort of handles the rest, right? During the break, you can take a look at the rest of this notebook. It has some tips. We talk about moving, so all these vectors, a lot of times they're moving in time, right? For example, theta, if I flap open my laptop over time, it varies with time. So we're going to take two derivatives of the position to get the accelerations, and you have to be very careful about tracking how to take the derivatives with respect to different reference frames. All that's done for us if we properly define the vectors as we've been doing so far. You can use, as you see, if you have a given vector, you can differentiate it, and it is completely aware of all the reference frames involved when it takes those derivatives. And that's one of the nasty parts. Like if you see this formula here, you have to do a lot of details in making sure that you are taking the derivative in the reference frame that you want to when you're forming the equations of motion of a general model. So it's going to handle all that. All the reference frames are aware of their angular velocities and angular accelerations once you define the positions properly. And this talks a bit about that. For example, if I provide it with a time-varying theta, right here I have theta is now a function of time. I can take the derivative of theta, and when I orient two frames given theta, I can then ask for its angular velocity with respect to another frame. So here I say, give me the angular velocity of B with respect to A, given that this orientation was defined. And it'll automatically take the derivatives properly for you when it computes these. Brandon's going to talk more about this when we actually build the model that we're going to build. Okay? So you can have a look at the remainder of this over the break. We'll take about 10 minutes and come back. A couple other details too. Robbie's going to talk more about adding inertial properties to objects. So we have rigid bodies. They all have mass, and they have a distribution of mass that you have to define too. And we'll talk about that. And then lastly, all these rigid bodies can have forces applied to them. And those are also simply defined by vectors. So you all have learned how to define vectors and how to specify them with respect to reference frames. And we're going to now take that and build a real problem and see it move and also try to control it. Okay? Okay, so we'll come back at 3:30. Take your red note and your blue note, and on your blue, give me a positive thing about the first part of the session, and the red, give me a negative. We'll have a look at those, adjust accordingly during the break. And if you have any questions, come and talk to us, and we will see you here at 3:30. Thank you.
Now that you've got your refresher on physics and some higher level dynamics vector stuff, we're going to talk about how we're going to set up a problem that we're going to work through the rest of this afternoon. Basically, we're just going to set up the geometry and talk a little bit about what sort of pieces we're going to talk about in later sections. So the first thing is the model we're going to look at is a two-dimensional, so we're not going to look at the full 3 dimensions. We're still going to have cross products and things that end up having vectors in the other directions that represent torques and things, but all the motion is going to happen in 2 dimensions. So we're going to basically build 3 bodies, and I'll kind of bring those up here so you can see them. If you pull through the notebook there, and we're basically going to develop this model of sort of a human standing. His foot's going to be kind of nailed to the floor, so it can't move. But with torque, he supports that lower leg, the blue section. And then at the knee joint, so that's going to be point A, that pivot point. And we're also going to have a mass center. If you can see the little, I guess, like crossed beach ball looking thing in the center, that's where we're going to say the center of mass is. And all those are going to be located directly in between the 2 pivot points for simplicity of this model. We're also defining length of those from the pivot points. So if you can see there, the lower leg, you're going to see DL is the distance from A to the midpoint of that section. And then LL is going to be the full length of that body. Does that make sense to everyone? Secondly, we're going to basically build upon this, and there's going to be torques acting at each of those joints I'm talking about, like A, K, and H, to control the segments relative to each other. So that'll be like the forcing component of this. And that's sort of demonstrated in the second 2 diagrams over there. So with each of these bodies, we're going to attach a reference frame to each. You're going to have one inertial reference frame, like Jason talked about, a Newtonian reference frame, sort of where we're going to look at how everything behaves relative to like normal physics that you're used to. Each rigid body from then on is going to have its own reference frame attached to it. Do you use any other reference frames along the way? Each one. So then we're going to have those 3 extra reference frames for each of the rigid bodies. And when they rotate, all the vector magic that was happening before will happen, and you can express any motion of each piece in whatever reference frame you choose. So when you have rigid bodies moving, they all have sort of like a mass and inertial properties, which are going to affect how they move. And basically, one mass we're going to think about is sort of a resistance to forces along a linear motion through the center of mass. And then inertial is going to be a resistance to forces that try to twist or turn that body around its center of mass. Another thing to keep in mind is the gravity component is going to be in the negative y direction for this model. If you can see the coordinate system labeled on the bottom. So that'll be a force that acts linearly through the center of mass of each of the rigid bodies. And then, as I mentioned before, there's going to be 3 torques acting at each joint, basically forcing the 2 rigid bodies apart, or not apart, but turning them relative to one another in the 2 dimensions. Is there any questions about that general setup of the problem? And then I'm going to turn it over to Brandon. Anything else I should mention?
All right, we're going to move on to the next notebook. This one's going to be how to code basically everything that Robbie just said and set it up in 3D space. So we're going to begin by bringing in all of the SymPy features and initialize the printing. And we're going to start with the reference frame. So we're going to have a reference frame for the foot, which is going to be considered the inertial or unmoving reference frame. And then, as Robbie said, we'll have one for the lower leg, upper leg, and then the torso. And then we'll set them up just like we did in the first notebook. So just one one frame per reference frame call, and then the 3 different labels for them. We're going to define each reference frame with a rotation theta, where theta 1 is the rotation from the ankle to the position of the lower leg. Theta 2 is the position of the upper leg from the lower leg, and then theta 3 will be the position of the torso from the upper leg. So now that we have our reference frames and our angles made, we're going to orient them as was shown in the first diagram. This time we're using the orient method rather than orient new, like was used in the first notebook. Okay. So in here we've oriented the lower leg frame in the inertial frame with the axis theta degrees or theta radians around inertial z. So exactly the same as we spent in the first one, or in the first notebook. Here's the direction cosine matrix for it in the inertial frame, and then in the lower leg frame. So you can determine the direction cosine matrix in each reference frame. Next, we're going to do the knee joint. And this is the upper leg to the lower leg. And so we're going to, again, orient them using theta 2 about the lower frame z. Let's see if I can scroll this. There we go. And so if you notice from the figure, we could use the inertial frame z or upper leg z's. All the z's are parallel to each other. So this part goes kind of quick because it's the same thing for each leg. Here's the direction cosine matrix from the upper leg frame in the inertial. And simplified, it becomes a different trig. Now we're going to take an exercise where we're going to create the torso reference frame and orient it relative to the upper leg frame. So like we just did with the lower leg frame to the ankle or to the foot, and the upper leg frame to the lower leg frame. And then just a reminder, I think Robbie passed out new Post-it notes, so put the blue one on your laptop when you're done and red if you're having problems. And if anybody still needs them, Robbie will come around. All right, we're going to go ahead and keep moving forward. So can see, we just create the reference frame and then the orient command. And then we can simplify it and run or show the direction cosine matrix like we did with the previous ones. So now we're going to move on to points and locations, and this part's newer in that we're actually going to start translating. I know there's some questions with the reference frames about how do I translate the reference frame's relation to each other. Well, the reference frames don't have translations to each other, but the points do. So we're going to start by making a point at the ankle using a point object from PyDie. And then we'll make one for the ankle, and then one for the knee, and then we'll make a symbol for the lower leg length and use that to define the position of the knee point with respect to the ankle point. So in this case, we're considering the ankle point as our starting point, and we're going to build up the rest of the model from there. So the way we do this is on the knee point, we use set position, and so we're telling it what point we're setting it from, and the magnitude and direction. So we've got our lower leg frame from earlier. We're going to put the knee point along the y direction of the lower leg frame at a lower leg length. So now we have the knee point set to the ankle, and we've got a method that you can see if it worked properly. It'll show you the position of the knee from any other point that you have currently defined. And then the lower leg frame was separate from the inertial frame, and so we can express this position in a different reference frame if we want. So here we've expressed the knee point relative to the ankle in the inertial frame. And then same idea, we're going to use the upper leg length to define the magnitude of the distance from the knee to a hip point. And then we use the hip point setting the position. We're going to go from the knee to the hip in the upper leg frame, the y direction, with an upper leg length distance. And then again, we can see the position from the ankle. And so we've built up the ankle to the knee plus the knee to the hip. And again, we can express it in the inertial frame. And we're using SymPy here to reduce the complexity of the trigonometric functions. So now we have the points for our human model set up in our different reference frames with one reference frame for each body. We're going to now add the center of mass location. So it's going to be same idea. We're going to, or I guess you're going to, set up the points and then the distances. And so I'll let you guys go ahead and start with that. Blue means you're done. Yes?
Why don't reference frames have translation?
Because in the reference frame, they each come with 3 direction vectors, and those are free vectors. And so if this is the x, y, z, this one over here is the exact same because it's got the same magnitude and direction, and they're not dependent on where they're located. Is that?
Yeah, so nothing's happening in that homogeneous component of the transformation?
So sometimes this is just a semantic thing with how we.
Hold on, Jason.
Our reference frames just describe orientation, and the points describe location. Some software packages that are similar might have origin and have translation associated. You can repeat that, I guess, repeat the question.
The question was, why don't the reference frames have translation? And what were you saying, Jason?
Just to repeat, in our software, we've decided to use reference frames to describe orientation, relative orientation, and points to describe relative position. And we could create, we just don't have an object that sort of combines those two. That might be a translating and orientating reference frame.
If there are no other questions, go ahead and begin the exercise. So here we just set up the center mass length and all these different lengths as symbols. So I'll scroll over some. And then we created a point for each mass center and then used the set position method for each. So the lower leg mass center is located from the ankle going up the lower leg center mass length in the lower leg Y direction. And then the same holds for the upper leg mass and the torso mass. So if we click on it, it shows the different positions of the centers of mass from each one. So here's the center of mass position from the ankle for the torso. So you've got ankle to the knee, knee to the hip, and then hip up to the center of mass position. And then while working, someone asked a question on dynamic symbols, which I had meant to go over more earlier. So when we defined the thetas, we didn't use the SymPy symbols function like we had in the past. We used dynamic symbols. So in this case, they're actually all functions of time. And so the background code knows when taking derivatives and integrating that these symbols, you'll need to have some correlation with time as they work. I forgot to point that out earlier, sorry. They will be state variables, but we're about to define 3 more. So now that we have, yes? Yeah, so position from is just a display method, and then set position is the one that puts the point somewhere. Okay, any other questions before I move on? Okay, so next what we're going to do is the kinematical differential equations. And to understand what we're doing here, I'm going to go back to F equals ma. So normally we use a equals the second derivative of the position variable, but we can generalize it to where the position variable derivative is not the same thing as acceleration's integral. So the speeds here, we will have that, but in general it doesn't have to be for our function. So we're going to set up, here it is. So theta dot is equal to omega n, and then we're going to use the derivative of omega in order to define our equations of motion. And so in this case, we've got omega n equals theta dot. And to show this, we're going to create a list where we're going to, each item in the list is an equation equal to 0, defining the kinematical differential equation. So we've got omega 1 minus the derivative of theta 1 equals 0 for the speed of the rate of change for the ankle to the lower leg, and then same for the next 2. And so those are the omegas are the other 3 states that from your question earlier. So this is going to be used by our equations of motion generator. We're going to use Keynes' method. I don't know how many people may have heard of Keynes' method, but he generalizes the speeds in order to come up with more convenient equations of motion depending on how you define these speeds. So now we've got the reference frames and the points all set up. So now we've got a static idea in the code of what this model looks like. So now we need to define how it's moving in the model. And so we're going to start by setting the angular velocities. Let's see, so lower leg frame is moving with omega 1 in the inertial frame z direction. And then angular velocity n, just like position from, is just a display method. So you'll set the angular velocity with this one, give it a reference frame, and then a vector, so magnitude and the direction. There we go. And so now we've got the angular velocity of the lower leg set up. So now as an exercise, set up the angular velocity in the upper leg frame and the torso frame. It looks like right now most people are done, so I'll answer your question as we continue moving. Like I mentioned earlier, the z's for every reference frame are pointed out of the page, and so the rotation is going to be in the same direction no matter which z you use, because each of the z vectors are equivalent. Does that answer your question?
It seems lazy or lucky based on the way the problem's defined. From what you said, it seems like the more correct way would be use a frame that you're directly attached.
You could if it's 3D motion, but just, yeah, like you said, the setup of the problem, it's a 2D plane, and so it doesn't matter in this case which Z you use. But in general, it probably would be better practice to use the Z of each joint. So now that we have the angular velocities set up, we're going to define the linear velocities. And to do this, we're going to define the velocity between 2 points in each rigid body. And so we're going to start by setting the velocity of the ankle equal to 0. Make sure. All right, so the ankle point is going to be our inertial point. It's going to be the point that's not moving in our system. And then from the ankle to the knee, we've got this formula here that defines the motion between 2 points in a rigid body, given the velocity of the first point and the angular velocity of the rigid body itself, or in this case, our reference frame. So we've already defined the position between the points, the angular velocity of the reference frame, and we're going to build up the velocities of each point at a time. And so we're going to begin with the center of mass velocities. So in this case, the V2 point theory implements this behind the scenes, and then the vel method is just a display method to show us what the velocity of the mass center looks like in the inertial frame. And then we do the same thing for the knee, upper leg, hip, and torso mass center. And so now what we have is the whole model where we've got everything in space, put a position correctly, so all the points are positioned correctly. They're all going to rotate based on the dynamic symbols that we put in. And they're all going to translate as we want them to. So now we've got the whole model set up and ready for the next step where we're going to define the inertias, unless anybody has any questions. Okay, I'm going to pass over to Robbie.
So the question was, again, why are all the angular velocities set up around the inertial frame? And that's because everything's rotating about the same z-axis. Does that make sense to everyone? In more complex problems, you would actually define it relative to different reference frames. And like Jason said originally, all the vectors can be represented in any reference frame you want them to be represented in.
Why do you need to define the kinematic equation? It didn't seem like there was, that code was referenced anywhere downstream from where it was defined.
So we're going to use it in the next notebook. That's why it hasn't been referenced yet. And it basically, the method that we're using, we sort of set up. It'll happen. You'll see how it's used in a couple notebooks away. But we are just simply specifying the those relationships to put the equations of motion in first order form. F equals ma is a second order differential equation, but all numerical integrators require you to put those equations in a first order form, and these are sort of a precursor to just setting that up.
So the question was, why did we set up the kinematics equations and they didn't seem to get used in that notebook? And that was an explanation of that. Next, we're moving on to inertias. So at the beginning of all these, they import all the information you need from the previous notebooks. So if you run the top sets of code, you're guaranteed to get all the right numbers from the previous notebooks, which I don't think we covered yet and explained to you. So you can start with any notebook anywhere you want, as long as you run the top bits first. So first thing to talk about with inertia is, I explained this a little bit earlier when we were setting up the problem, but you have a center of mass, and if you act with forces through that center of mass, you basically get linear translations, and the mass is sort of what resists that force and against you, or a change in that position. The inertia, rather, is like the distribution of the mass in an object, and so depending on size or shape, say like a marker, if you push on it down low and you don't have any other forces on it, it'll translate and rotate, right? Like if you imagine it kind of in free space and you push it on the bottom. Based on that inertia, we'll decide how much it decides to rotate or how much it resists that. If there's a lot of mass toward the outside edges, it would rotate less than if all that mass is at the center of the object, if that makes some sense. So running through this. So first thing we're going to do is import like inertia and rigid body from the SymPy physics mechanics. And we're going to import symbols. And talking about mass. So here we're going to create symbols for each of the masses for the lower leg, upper leg, and torso. And then you get a symbol for the lower leg mass, upper leg mass, and the torso. It's pretty simple. It should be kind of what you expect. The inertia is a little more complicated. And so for each piece, we're going to create the symbols for these as well. And what we get to is this piece we call a dyadic, which is basically it's sort of a unit tensor, and that's to say it's sort of the more complex version of how each bit affects rotations in the other axes. Does that make some sense? So instead of a dot product where we get like a scalar and you multiply and add everything up to get sort of the action in a certain direction, this is going to more separate out all those unit vector acting at a moment from the centers and all around a certain axis. Because of the simplicity of this problem, we're going to get a very simple set of these, which is going to basically relate to almost exactly the unit vectors. So here's the first example of those in a matrix form, and you notice how, because of the simplicity of this problem, you're only going to get the one term at the ZZ position. Get the same thing for the upper leg. So that was the first one I did was the lower leg piece. Do the upper leg. And then as an exercise, we ask you to create the dyadic and the central inertia for the torso. Reminder, put up your blue stickies as you finish. And I should also note this is defining rotations about its center of mass. Not so if you do rotations about a different point, you get a whole different matrix and tensors related to it. Okay, so for this we create a. All right. But it has an error. I gotta create all these, all right? Oh, okay, okay. Okay, so first you create the torso initial dyadic by doing inertia of the torso frame as its parent, 0, 0, and then torso inertia, which you defined up here in the same way you do in the for the upper leg and the lower leg. So first one's created here. So if you do those in the same way, coming down. So then we also want to create rigid bodies attached to all of these. And that's another exercise. Did you guys run this exercise too, or no? You did? So that creates a rigid body for the upper leg and the torso, which has a center of mass at the place where you decided the center of mass was. And it has the mass of the upper leg's mass, and it also has the inertia of the upper leg's mass. So you basically created an object like the pen that's now named upper leg, has a center of mass where you defined it earlier in the kinematics. It has the mass that you defined in this section and the inertia you defined in this section. So it will spin and move just like we want it to. And now we're moving on.
Okay, so these next two notebooks, we're going to try and move a little quicker so that way we can get to the visualization before we run out of time. In this notebook, we're going to set up the loads on the system. And so we've got the gravity force and the negative y of the inertial frame. So the way we're going to use forces in this, we've got the symbol G to represent the magnitude of the force. And then we put it in the negative inertial frame, so mass times gravitational acceleration, and then in the frame. And then for the actual force that we're going to pass into the equations of motion generator, it's going to want to know the point at which that force is acting. So we're going to take that force that we just made and put it in a tuple with the point for where the force is acting. And then we add the gravitation force to the upper leg and torso. And then the only other loads on the system we have are the joint torques. And so the ankle has a torque. Let's see if there's images. Yeah. So we've got the torque on the ankle, the knee torque, and the hip torque. So the ankle torque acts on the lower leg, and we're going to do counterclockwise positive. And then we're going to have the torque of the knee act positive on the upper leg joint. And so by Newton's third law, we have it negative here. And so equal and opposite reaction. We've got the torque set up for ankle torque and the inertial Z, and then subtracting out the knee torque and the inertial Z. And like we mentioned earlier in the tutorial, you could use other Z reference frames or Z directions, but it's a 2D problem, and so all the Z's are equivalent. And then just like the force, where it wants to know where the point is that the force is acting, the equations of motion generator want to know what frame that the torques are acting in. And so we're going to create a tuple for each of the torque that each of the bodies are experiencing, where we have the frame first and then the actual torque vector itself second. And the same idea for the upper leg, where we've got the knee torque in the positive and then the hip torque in the negative. And then we put it in a tuple with the reference frame that it's acting in. And so lastly, the torso torque goes the same way, except this time it only has the one component because there's only the hip torque. We don't have a second torque on the top. And they're all acting in the Z direction. That was kind of quick if there are any questions. All right, I'm going to move on to the next one. So here we actually set up the equations of motion. Like Jason was mentioning earlier, this is where we're going to take into effect those kinematical equations from Notebook 3. So we're going to use Keynes' method, and here in the tutorial we've got it pulled up where you can see the docstring of Keynes' method and the sort of arguments it takes. And Jason's currently working on an overhaul of the docstring itself, but we're going to keep moving forward. So what it's going to want is the coordinates and the speeds. And so like we mentioned earlier, both of them together comprise the state, but in the equations of motion generator, we're going to put them in separate. So we've got the thetas for the coordinates, and then the speeds are the megas. And then we've got the kinematical differential equations that relate the derivative of the coordinates to the speeds from earlier. And we're pulling that in from Notebook 3. Now we're going to actually set up Keynes' method object. So we give it the inertial frame, the coordinates, the speeds, and the kinematical differential equations. And this object has the ability to be a lot more complicated with constraints and more complicated speeds. But we're going to keep it simple for this. So now we've got a Keynes method object, which is an algorithm for defining the equations of motion, which is F equals ma. And we're going to use those for a simulation later. But when you run Keynes method, it doesn't calculate the equations of motion yet. First, we put all the loads into an iterable. So here we're going to put them all on a list. So we've got all of the gravity forces and all the torques that we just defined quickly last notebook. And then the other thing that it's going to want is the bodies. And so here we've got the lower leg, the upper leg, and the torso, or the rigid bodies in the system that Robbie defined. And so now we can actually run and get the equations of motion. So we're going to take that Keynes object that we just created and run its Keynes equations method. So we give it the loads and the bodies that we just defined, and it'll create the equations of motion. So we can have the equations of motion as F equals ma and T equals I alpha, but the way that Keynes equations produce them, it gives us this FR and FR star. And so our object will return these two, and it's going to display. Okay. So while it's simplifying, I'll keep going. There are other ways that you can access these equations of motion after you've run Keynes equations. And so you can get them where, here it is. So you can see they're rather complicated. And that's after simplifying. And so we can get them in a form where F equals MA. So M will be accessible as a mass matrix from the Keynes object after Keynes equations have been run. And then you can get F as a forcing vector. So we've got all of this down here. So we've got mass matrix and mass matrix full with Keynes method, and same thing with the forcing and forcing full. And the difference between these two is the kinematical differential equations. So in the equations of motion, those aren't necessarily included, but you'll want them for your ODE, because you're going to want that in order to get your states or your coordinates. And so mass matrix full includes the kinematical differential equations on top of the normal mass matrix. And forcing full will include the other side of the kinematical differential equations on top of the normal forcing vector. And so while these load, the kinematical differential equations in this case, because we've got omega equals theta dot, the mass matrix is just going to be an identity matrix, because each omega corresponds directly to the theta dot. And then the forcing vector should be the theta dots. So yeah, or omegas. So you've got an identity matrix right here to say that theta 1 dot equals omega 1. And then underneath it, it's the F equals MA. And then, are there any questions? I'm sorry we went kind of quick, but. Okay, I think Jason's up now.
Okay, that was a bit of hand waving. We're hoping to get to the numerical part and the visualization part, which are the last two notebooks I think we're going to get to this time in the tutorial. Just to reiterate here, we created all of the kinematics of the problem, right? Those are the positions, the velocities, and passed them to, and then we created the kinetics, right? Those are the torques and the gravity forces acting on this system. So once we have the torques, the kinetics are the F, right, in F equals ma, and then the positions and velocities are going to help us get the A. And then Robbie also had the M part, which is all the inertial terms. So those are the three pieces we need to get the equations of motion. And Keynes method is a class that takes that information. It does some magic behind the scenes, which you can read about in our documentation if you want to know the details, but essentially takes that information and formulates the final set of equations of motion, F equals ma. All right? And this big mess that he shows you is what that is. You know, and it's something that you really wouldn't want to do. You don't really want to do by hand. People do them by hand. But the power of this tool is that you can specify simple description, and then it will generate this nasty mess for you. Okay? Once you have that, we want to now go to numerics land, right? We have a symbolic description of the equations of motion of this human system that we've been working on. And in general, that can be put in a form as you see right here. It's a first order ordinary differential equation. And we in particular are going to use this form, which is m x dot equals f. And those last two pieces are m and f, right? It's a matrix that's linear in x dot, which is the derivatives of the states, and the states are the coordinates that we had, the thetas, and the speeds. And so we can take this symbolic description and now open up a new notebook, simulation, and we're going to use numerical values to integrate that ordinary differential equation, or set of ordinary differential equations, and see how this thing moves. Okay? So open up the last, not the last notebook, but notebook 7, and we can go through that, okay? So notice in the imports, we're going to start bringing in things from NumPy, right? So we can do numerical things, and SciPy. In particular, we're using the ODE_int function, which is a numerical ordinary differential equation integrator. Finally, we're bringing in something from PyDy. PyDy has tools that convert the symbolics to numerics, right? We want to now have numerical functions that can evaluate the equations of motion rapidly at thousands or millions of times, okay? So we're going to bring in some functions from there, and we're going to do some plotting. So I'm bringing in matplotlib, some functions from that. And those are all the imports. So we've brought in a lot of the SciPy stack now, most of which is to do with numerics and plotting, okay? So we've defined a lot of variables in the system. We have a lot of constants, right? The lengths, the distances that we've described, the masses and inertia values, the acceleration due to gravity. We're going to put all of those together in a big list, okay? We also have the time varying ones, right? We have the coordinates, which are the thetas, and the generalized speeds, which are the omegas. These are our time varying variables. Okay, and then finally, we have one more set of time varying variables that are associated with our torques that are being applied. Those are going to be specified by us, and they vary with time. So take a couple minutes and make a list of those torques so that we can have them available to generate our numerical function. And give me your blue sticky note once you've got that list done. So we got Okay, so a fairly simple exercise. We just needed to create a list here of the time varying torques. They're what we're going to call specified. That's because we're going to get to choose what those are over time. Okay, so the next bit is that we're going to take this symbolic ordinary differential equation and we're going to use a function called generate ODE function to transform that symbolic into a fast numeric function. If you note that ODE int requires that we provide it a function that can evaluate the right-hand side of the first order ordinary differential equation. Okay? Generate ODE func, that's a long docstring. Generate ODE function takes the symbolic f that I talked about a minute ago. It takes the coordinates, the speeds, and the constants, all those lists that we created. It takes the big M, the mass matrix, which is also symbolic, and the list of specifieds. Everything that I passed in to generate ODE func is a symbolic thing, right? It's either a matrix of equations or symbols. So this is basically taking all of that information and it generates a function. And if I look at the type of that, right, it gave me a function. And then I can look at the help for that function. And it says this returns the derivative of the states. I.e., numerically evaluates the right-hand side of the first order ordinary differential equation of this form, where x is the state vector, and we see that it has theta 1, 2, 3, and omega 1, 2, 3. So there's our state vector for this first order ordinary differential equation. It also takes t, a float, a current time. It takes r, which there's a number of options how you can pass an r, but r represents the specified values. Those are the torques that we had. And then P is finally it's either a dictionary or the numerical values for this list of constants. And so if you recognize that those are the constants in the system, and then R is the torques. It returns the derivative of that vector at that given time, okay? So any questions here? What happened? So we had a symbolic form of a ordinary differential equation. We passed it to this generate ODE func, and it takes all that information and it generates a function that will evaluate the right-hand side of that ordinary differential equation. So let's see that in action. So I can say the initial condition, right, I'm going to create x0 as a bunch of zeros, right? This is a NumPy array of zeros. And then I'm going to set the angles to 2 degrees, okay? So now I have that theta 1, theta 2, and theta 3 are all at 2 degrees, and that omega 1, 2, and 3 are all at 0. That means no motion, but this thing is going to be configured at some orientation. Also need to pick some numerical values for all those constants, right? So here I've looked up in the literature basically values that represent the inertia, the lengths of the limbs, and the masses of an average human, okay? So these values are numerical values that represent all of those constants in the system. So we're also going to need to supply some numerical values for those torques. And for our first simulation, we're just going to say the torques are 0 through the whole simulation and see what happens. So for this exercise, create some numerical specifieds, similar as we just did above. And then also create a vector using the NumPy linspace function that gives us a vector of times we would like to evaluate this over. And we want a time vector that goes from 0 to 10 seconds and samples it at 60 hertz. So take a few minutes and create those two vectors, and give me your blue sticky notes when you're done. I got 18 left. So we've had one error with SciPy 17 on Mac. So if you're having that error, you could downgrade to SciPy 16 and it worked. So this is a relatively simple exercise too. In the interest of time, I'm going to go ahead and give the answer. And actually, I probably didn't describe that very well, but I created an array of zeros of length 3 for the torques to be 0 in the simulation. And I created a dictionary here that contains the numerical values of the constants and those specified torques. And then finally, I used linspace to create an array of time that goes from 0 to, that doesn't match, 10 seconds should be 5 seconds. But anyways, this goes from 0 to 5 in my solution. So I've got a small error there, and at the correct sample rate. So once I have all of that information, I can now evaluate that function we created. The right-hand side function takes the state vector, it takes some time value, and then it also takes the numerical specifieds and the numerical constants. And note that that output is now the derivative of the states according to that ordinary differential equation given the current state. Okay? So I have a function that I can use in ODE int. So if I run ODE int and I pass that function there, I give it an initial condition that the object is in, and then I pass in the numerical specifieds and constants. Y, in this case, is now an array of the trajectories of all 6 states through time. So ODE int integrated that equation to motion, that ordinary difference equation, and now it gave us the trajectories. We can visualize this by plotting the results. So I have a few matplotlib commands, and I just plotted the first 3, which are the 3 angles, theta 1, theta 2, and theta 3. What does it seem like is going on here? Any thoughts? So we've started the we set the angles to 2 degrees of this pendulum, so it's sort of off kilter a little. We don't apply any torques at the joints. We let it go. And what happens?
Same thing we've seen in the videos in the SciPy class.
Falls over. Yeah, so these angles are huge, right? I've plotted it in degrees. It's going around and around and around. Okay, so we don't have any kind of constraints that prevents the knee from not going too far in the wrong direction. And this model is a little weak, right? When we fall over, we do a little bit different. But in this case, we do have something that's moving, right? We see change over time. And I am going to skip that last exercise. It's just the same plot of the angular velocities, the other 3 states, and you'll see that they sort of go crazy too. Okay? So to recap on what we did here, we took the symbolic form of the equations of motion, this ordinary difference equation. We converted it to a function that can evaluate numerically. We stuck it in the numerical integration routine, ODE int, and simulated the system over time with no torques applied, and we've got some motion here. Okay? So I'm going to give it to Robbie. We've got 30 minutes left. We're not going to get to the control notebook, so you get to do that at home. But the next notebook, we're going to see how to visualize and picture what's going on a little easier than a simple plot. Okay? Any questions before we jump to that? No? Okay. Robbie's up.
You hit the timer. Okay. How do you get rid of all these, Jason? All right, we're going to do some of the more fun stuff now, I think. So what we're going to do is basically draw out some of the pieces and what we want it to look like as we go through. So we're going to import our old stuff. So we got that picture. We're going to try to draw this as best we can. So we import, so one thing we're going to do is from PyDi viz shapes, we're going to import a couple of shapes to use to help us draw these pictures. And then I've also listed a bunch of shapes that you can also use. They all kind of come up differently and oriented in different ways. So you've got to kind of learn each one for now. We're also going to import a scene object and the visualization frame. So the first object we're going to talk about is a sphere. And so if you bring that up, you have to tell it, you can name it basically, and then the size of it. And then with the arguments, you can place it and tell it what reference frame you want it to be in. So here's a couple examples. We're going to say ankle shape, make it the color black, and have it radius 0.1, et cetera, for a knee, a hip, and a head. And then for their visualization frame, we have another object. We'd give it a reference frame and a rigid body argument, and what do we do with the visualization frame?
Associates the shape to the reference frame.
All right, so yeah, it puts that shape that we're drawing and locks it into one of our reference frames. And here's some examples for the ankle, knee, and hip. We give it, we're going to put these in the inertial reference frame. We tell it to ankle, knee, and hip. And we give it the ankle shape, knee shape, and hip shape. And then here we're going to create a new point for the head because we don't have that located in our object at all. So we're going to basically use some of our constants, the torso common length and the torso frame, to locate that point head relative to the hip. And then we're going to create the visualization frame for the head using its inertial. The inertial frame is the basis, the head point, and the shape that we described. So that sphere, we're going to place that sphere at the point. Next, we're going to locate a center for each of these pieces to tie new shapes to. So what we're going to do is, based on the length, decide a center point to actually put the pieces at. So the center of these cylinders that we're using aren't necessarily lined up exactly with the mass centers. So we're calculating here where the actual center geometrically is between the 2 points so that we can draw pieces to make up the actual rigid body of that represents the rigid body of the legs and the torso. And then we have a dictionary to help us out with the numerical constants. Whatever. Oh, because I think we're assuming that the head is actually twice the distance from the center of mass up, and then we're just going to use the center of the cylinder at that one actually does line up exactly with the center of mass. Does that make sense? Okay, now we're going to use a different object called the cylinder. And like I said, you can name it. It has a length and a radius. And then you can also place it relative to a reference frame. And I think there's another piece in there that we use. You'll see in the next set. So here we're calling it. So we're going to create a cylinder with the radius. It's using that lower leg length. And so we're going to color this one blue. That was the other argument that we're going to use. And then we locate it with the reference frame as the second part of that command. We're going to do that for the upper leg and the torso as well. Anybody have questions? Then we're also going to create a scene. And this is just sort of a space in which we can look at all the stuff. We can name multiple of these. So if we wanted to look at one set of pieces at a time, you could create one that just has the lower leg and the upper leg, and then one that has just the upper leg and the torso together, and look at them all move around differently. So we named this, we give it a reference frame and an origin to basically draw everything about. And so here we're creating a scene using the inertial frame and starting at the ankle point as the origin. And here we're deciding which pieces we want to see in this scene that we're going to look at. So we're going to look at we need all the reference frames, all the visualization frames, rather, for the 4 actual leg segments, and then the 4 spheres that we gave the ankle, knee, hip, and head. And so here we're bringing in the states so that it knows how to move all of these things from the calculations Jason just did, and the trajectories. And then from there, we can use this magic command, the scene display IPython. And it brings up a little drawing of what we're looking at. I'll try to get it where you can see it all. And so you watch it fall and kind of tracing out all those angles that Jason just showed us in the other graph and why it looks so crazy. And watch it fall again. So this is sort of example of what a lot of people describe as chaotic motion, I guess. So a fun exercise. We're going to try to create a nose and put it on the head and make it move around so it actually is part of the head. And you get to do all the making of everything. It's kind of more self-guided than some of the others. Anybody have questions? And I would say work with people on this one. And you might need other shapes. You can use other shapes. You could make, I don't know, you can make a duckbill nose. Do anything you want, have some fun.
So I'll just say, too, we're going to take just about a little over 15 minutes for this, and then we'll have a few minutes to close, and then we'll all go home or go to happy hour. So that's it. Okay, I'm going to type the fix here on the Etherpad. Okay, so that's hard to see, this line. Let me break that out. Okay, so this line right here, fix Jupyter. If you're Conda install Jupyter, IPy widgets, and Jupyter Notebook all less than 5, then the notebook should execute properly. That should fix you. I heard if you're using pip, you can do the same thing, but change that to pip. You might need to remove them first, I forget. Or it might be pip upgrade, and you can specify that.
It's pip install, name of the package, double equal, and then the version number.
Oh, yeah, that's if you want a specific version.
And you might be able to do less than version.
Yeah. You probably have to put it in quotes if it's a less than. You could also do equal for, something like, let's see, pip. If you just do a single for, it will get the latest version for.
You might want to not do Jupyter, but IPython less than 5.
Yeah, Jupyter's wrong right now.
Oh, Jupyter. Oh. This is 1.0 Jupyter? So what is it that it would be breaking here then? IPython notebook only?
Actually, that's not true. I downgraded my Python to 4 and it still didn't work, so I might have to downgrade Jupyter as well.
The key thing is, I think the key thing is this IPy widgets. Maybe if you just do this. So we use the IPython widgets there, and they just upgraded to 5 today, and that's breaking it. I think that's the fundamental.
We have the 4.1 for IPy widgets, actually, so they're under 5.
And it's still breaking?
It's not that it breaks, it just doesn't, it runs and then nothing appears.
After you install 5, downgrade to 4, it still won't work too. I ran into this when it got upgraded a few months ago. It installs new extensions of your old ones that don't get downgraded when you downgrade.
Ah, jeez. So do you have a suggestion of how to fix that?
Yeah, I blew away my entire installation.
So maybe you want, so if you're using Conda, you can create an environment. Just do Conda create, we'll name it I love IPython devs. And then you can do NumPy, IPython notebook, maybe SciPy, matplotlib.
You might still want to specify some versions because that's what I did when I set up my current environment.
Yeah, I was going to do just widgets, maybe widgets less than 5, and that's got to be in quotes. IPy widgets less than 5. What else? That might work. So you could create a new environment, and then then you have to, on Mac and Linux, you have to type source activate that's supposed to be love IPython devs. And on Windows, you would just type activate. So that could create a new environment that should be completely clean, that will force IPy widgets to be less than 5. How many people is this not working for? 1, 2? Okay, well, that's not too bad. We can come help you too.
I'm attempting to check those.
robotic systems that are actively using this library. So the question on are there complex robotic systems that are actively using this library? I don't think so. I use it for my research. A few companies I know use it for some applications, but I don't think it's running any kind of like dynamics engine or anything. Does that answer Matt's question? If he wants to identify himself. Yeah, I can tell you more about it later if you want to. So we got 5 minutes left. I apologize on the final that final notebook there with all the errors. I don't know, did anybody get a nose? Yeah? You got a nose? Do we have, we got this, you want to come show your nose real quick? Yeah, both of you, if you want, see what you got.
Can we vote on the better nose?
Yeah, we can vote on the better nose. Let's, here's your Mac.
No.
Oh, what do you need?
HDMI?
Try that. And what's your name?
Alan.
So we got Alan here, and he looks like he successfully put a nose on the man, or on the person. It's a very cute nose. Yep. Okay. Nice work. And then you want to show yours? Let's see what kind of, thank you, Alan. What connector you need? This? You need HDMI too?
Mine's more of a, less of a cute nose, more like a giant bird.
And what's your name?
Chris?
Chris. So Chris has less of a cute nose, but a giant bird nose. Are we getting connection? Did I touch something?
That's okay if it won't connect.
No?
That's okay.
That's okay. So let's describe it. Describe it to us verbally.
Well, you can see it's really beautiful here. It's got quite a large nose, and then it spins around, I think.
All right. Very nice work. Thank you, Chris. Okay. Just a few minutes left. Thank you all for attending. I hope that this has been very informative. Sorry for few of the bugs. We've got a couple minutes left. If anybody has any specific questions, we could hit any broad or general questions. We'll be here after if you want to chat, and we will probably go to happy hour too if anybody wants to join. We'll find some place nearby. I don't know, is there anything else we wanted to say? The Post-its. Okay, when you leave, please give me a positive and a negative on the red for negative, but blue positive. Again, we'll take that and try to improve the tutorial for next time we give it. We changed up some things a little bit and didn't quite get to the last notebook either. So there's one more notebook that you can go home and check out. It shows how you would use SciPy to build a simple controller that will make this person stand up using the torques at the different joints. Okay, so you can get a little control there. I can actually just probably show you really quick the result. It's maybe not as exciting to look at as the other, but I'll ignore. What is the exercise? Let's see what we got. I'll just show you the visualization at the end. But this is a rapid fire control algorithm. And we see that the plot's not all chaotic now, right? It starts at some configuration and then goes to a 0 angle, and then if you put those new trajectories in the scene, you can see that this character will, instead of fall over, will stand back up, okay? So that's not a very elaborate, but you can tweak the numbers and see it sort of behave differently. But in general, there's one more notebook that will show you how you can apply some control algorithms to this dynamic model that you've created. Okay, so I apologize we didn't get there quite there, but I hope that you all learned a lot. Any final questions from the audience? Yes.
Would it be possible to incorporate non-analytical elements into the model, such as dimension contact algorithm?
Yeah, it's not straightforward. We don't have like very pretty ways of doing that, but you can basically output all the parts of the dynamic model that we've done. You can spit them out into whatever language you might like to work in, from Python to C to Fortran, and then you could tie in whatever contact algorithm to generate forces that you would want, whether that's like some separate library. This would be a lot of custom work, but you've got all the pieces fully accessible that you could connect. To make that nice and easy to do would take some work too. That answer you?
Is the solver, is it explicit?
So
Explicit or implicit?
the one that just happened there is an explicit solver. It's just, you can choose any solver you want, right? We have a default. If you wanted to use a variety of other integration methods, you could plug those into.
So they come from some other library?
They come from other libraries. We don't write the solvers. We use tested libraries that are, smart people write them that are smarter than me.
So you can just say, there's some way to say, call this function here in the loop, and have it evaluate the contact problem or whatever problem.
Correct.
And
Correct.
It has no problem with that.
Yeah. I can, if you want to chat afterwards, I can give you more detail about how something like that might work. But yes. Yeah. Any other questions for the tutorial? No? Okay, well, come chat with us afterwards, and if anybody wants to hang out, we'll chat. Thanks again for coming, and appreciate your hard work.